Yeah, I guess this is a case of the cobbler's children's shoes are never mended. I'm never done with my heating system. But we're inside the home now, and you can see the air handler. I've got my documentation in that little folder there, so I know where it's at, and some extra modules for my PLC there. This is actually the PLC right here I'm pointing to that controls the system and accepts commands from the thermostat, requests for heat or cooling. And then this PLC actually makes the decision of whether to pull heat from the boiler or turn on the heat pump. And it depends on the temperature outdoors, depends on how much heat the system is calling for, because that heat pump can be in a high or a low mode. It depends on whether the boiler is ready. Does the boiler have hot water in it that can warm the home, or do the tanks that I've got have hot water in them that can warm the home? Anyway, you can see the refrigerant lines running here, one copper colored and then this black colored one running to the side of the unit. Those run into the A coil. Now, one thing different about this system, because it is a heat pump, there's an expansion valve inside this next to the A coil. It's a thermostatic expansion valve. The classic way of expanding refrigerant is to use capillary tubes, but that's not necessarily the most efficient way to do it. It can't change. And so the thermostatic expansion valve inside here is used in heating mode because the refrigerant actually comes in. Let's see, did I say that right? I have to think about that. I can't remember if it's the thermostatic expansion valve in here. I'll know that in a minute. But anyway, the refrigerant comes in hot as a superheated gas in this black pipe. So it's at high pressure. And then yes, that's right. It goes through the A coil first, so that the A coil can remove heat from it. And actually, the only thing that can come out of the A coil in cooling or in heating mode is liquid. So you're taking the gas and you're condensing it. So you're removing the latent heat of vaporization from the refrigerant, but the refrigerant is still at a relatively high temperature. So after going through the A coil in here, like I said, there's a thermostatic expansion valve inside of here that then allows the pressure drop to occur, so that some of the refrigerant boils off. Now, yeah, that's right. I got to check myself. So some of the refrigerant then boils off, cooling it down, and goes through this return. You know what? I may be wrong. That may not be the case. I am wrong. The thermostatic expansion valve for heating mode is actually outside in the compressor unit. The thermostatic expansion valve in this unit is for cooling mode, so I'm wrong. So what happens is the superheated gas comes in this black pipe, goes through the A coil, is converted into a liquid, basically losing its latent heat of vaporization, and then goes back up this copper pipe and out to the heat pump unit. Now, when it gets outside, what happens is it goes through a thermostatic expansion valve where some of the refrigerant boils off and the temperature drops drastically. So now you've got a saturated liquid vapor mixture running through the coil outside, so that it is accepting heat and boiling off from the outdoor air, which you and I would call cold. But since the refrigerant is at an even lower temperature than the outdoors, it can be boiled off by the outdoor air and then go back into the compressor, recompressed, go back up to the high temperature because of the compression, and come back again into this pipe and continue the process. In cooling mode, the thermostatic expansion valve in here works, it's the thing that expands the refrigerant. So in cooling mode, what happens is that the refrigerant flow is flowing in the opposite direction. So instead of coming in this black pipe, the refrigerant is coming in this, it probably looks gold to you, but it's actually a little copper pipe. And the refrigerant is actually in a liquid form. It's still relatively warm, because what's happened is it's just come through the heat exchanger outside in the compressor unit, not through the compressor yet, but through the heat exchanger, where it is converted to a liquid. So it's all it's given up its latent heat of vaporization then to the outdoors, because it's in cooling mode, comes in here, and then the first thing it encounters is a thermostatic expansion valve where it is allowed to expand. And so as it expands, its temperature drops, some of it boils off, and then the A coil inside acts as an evaporator, takes the rest of the liquid, boils it off, so that the refrigerant is accepting heat from the air that's flowing through this. By the way, the airflow through this thing is from bottom. You can kind of see down there, that's the bottom of it. It's off the floor a little bit. Comes through the bottom, flows upward, and then through this ductwork here, which goes and feeds the bedrooms in the back of the house, and then ductwork you can't see that kind of goes forward and goes, the house sits front to back this way and side to side this way. So this this ductwork here and that goes on that way feeds the back and the front of the home. And then I've got, you can kind of see some of it there. My basement is unfinished, but you can kind of see an arm going off the side that comes off the ductwork that goes that way. Okay, so there's several of these. There's several of these ductwork arms that go off to the side and the other side of the home as well, off in that direction. Anyway, this is also an expansion tank right here. You saw the red expansion tank outside. This Amtrol expansion tank, you think, well, that's huge. It has a capacity of about 50 gallons. The reason for that is that my water storage system is 1,000 gallons of water that can be heated up. As that water expands, it also, of course, requires more volume. And so this is sort of an overflow tank is the way you can think about it. It's a place for the water to expand into so that, you know, it doesn't bust apart pipes, because the water will. If the water has no place to expand, it will find a place. It will make a place and expand as needed. Of course, the first thing to fail would probably be these PEX pipes. Even though they're very strong, PEX can expand quite a lot, and that would be the first thing. But it's limited in terms of how much, and with 1,000 gallons you could easily pop one of those pipes. What I'm doing to increase the system's efficiency and really monetary efficiency, this is my hot water heater. I'm adding the ability to heat my domestic hot water with the boiler. And so if you look over here, this blue and black thing, that's insulation over what's called a side arm. It's a heat exchanger that I've piped into my system so that eventually I'll have pipes coming out here, and there's one at the bottom you can't see because of my couch. But that's where the hot water from the boiler will flow through the heat exchanger, and then domestic hot water flows through the center of that. They're separated, of course, and can be heated. There's a pump down here. You probably can't see it. I'll try. Yeah, you can kind of see it. It's right there. It's insulated real well. But that pump circulates the domestic water, and it's actually a brass pump, that way it doesn't rust. But that circulates the domestic hot water from the bottom. I actually tied into the drain at the bottom of the water heater so that I could pump water through it, the domestic hot water, and heat it with the boiler. Now, I wish I had a thermometer here. I don't. If I feel these pipes, they're still pretty warm. And the reason they're warm is because the heating system was just on, and those pipes, these 1-inch PEX, actually go down to a heat exchanger right here that's on the bottom of the unit. Now, this is not the ideal place, because if you think about it, the heat exchanger down here has really hot water in it when the boiler is operating, and so air is carried across that heat exchanger, warms up quite a bit, and then hits the A coil. Well, what happens if by some mistake the heat pump is running? Well, then you got really hot air going through here, and heat will actually not flow this way, it'll flow the other way and mess up the heat pump. So anyway, I don't like that. I wish that my heat exchanger for water to air from the boiler were up at the top, but I just didn't have a way to do that. Now, of course, you guys know me, I'm going to try and improve this system as much as I can. Once I get the system set up for geothermal, I'm actually going to have to replace this whole thing. And when I do and put in a geothermal system, I won't have an outdoor unit. I won't have these refrigerant pipes anymore. Everything will be contained in a box about this size, and I'll be able to then put that heat exchanger that's down low up where it should be up high. So, you guys know me, the crazy thermo professor, always doing something with these things. I'll show you some of the piping now. Let me, my dirty basement. I'll show you some of the piping. This piping network over here is actually the piping that then goes out to the tanks. Behind that wall, that concrete wall, is where I buried two side-by-side 500-gallon propane tanks. And at the time, I wasn't sure if I wanted the water to run through one tank and then to the other, or if I wanted to run through both at the same time. Well, it turns out it's better to have it run through one and then through the other. And so I actually set up my piping network with all these different valves and things so I could isolate the two tanks from one another if one ever developed a leak and I couldn't fix it because it was the middle of winter, or if I wanted to pipe it where the water went through both at the same time or one after another. I actually set all that up so that I could change it. You can't see all the piping because I got some junk blocking it, but right there is a filter. It's a high temperature filter. You wouldn't want to use just any water filter, but this is a water filter that can operate up to, I think, about 190, 200 degrees, and it had to be 200 degrees or so. Anyway, I've also got a bypass network on this so that I can go around it, and right now I actually am bypassing that water filter. That's because I need to change the filter. There's too much pressure drop in it right now. I've also got check valves around it on either side to allow for bypassing and flow. I can't remember why I did that or how it was, but anyway, there's a lot of thought that goes into setting up the piping network. Now, I will show you guys everything that ties this together. You can't see it really well, but the piping that connects to essentially to the tanks. There's two pipes, one send, one return. It can actually flow in the opposite direction as well. There's a reason for that. I'll explain that in a minute. But this piping actually connects over through a pump here and through this pipe here to the main run, which goes out to the boiler. You see that heat exchanger right there? That is a plate frame. Well, it's not a plate frame, it's a brazed heat exchanger, but it's like a plate frame. And you can see my air separator here. There's also a pressure relief valve right there that's piped up. You probably can't see the pipe. Let's see if I can get a view of it. Yeah, you can't really see it very well. It's kind of hidden right there in the shadow. Above this pipe is where the pipe actually runs out to the garage and then out near the door, so that if this side of the system overheats or there's too much pressure, water can escape and won't hopefully flood the basement. Now, what's interesting about this, I showed you the piping outside in the boiler. You can't see it, but it's actually coming in here and out the other side. And then the other side of this heat exchanger is what's connected to everything down in the basement and the tanks. What's interesting about that is that this heat exchanger allows me to separate the water that's in the boiler from the water that's in the tanks, and essentially the water that's in the tanks is the same water that runs through the system and heats the home. Why would I want to do that? Well, think about how much it would cost to treat all of the water in these tanks with antifreeze. It's actually quite a large cost. And think about it, you'd have to do it. If it weren't for that heat exchanger, this water here would end up in the boiler as well. But what that heat exchanger does is separate the boiler water from the tank water. And so I've got 1,000 gallons essentially on this side of the system and about 50 gallons on the other side, maybe 100 on the other side in the boiler. I don't remember now. But it's a lot cheaper to treat that water out there, you know, if it's 50 to 100 gallons with antifreeze than to have to treat 1,000 gallons with antifreeze. And I'm not worried about these tanks because I'm actually down in my basement. My basement is below grade. The tanks are buried at least 4 feet, maybe 3 or 4 feet below the top soil line, so there's no way the water in there will ever freeze unless there's a serious change in our climate, which I don't foresee. Anyway, so basically the way this works is when the boiler's running, it can either supply heat to the home going through these pipes and then to the air handler, or it can take a turn here and supply heat to the tanks where the hot water is going down this way and then returning back here. It actually comes back into the system. Where is it? It comes back. There it is. It comes back into the system right here at that T. You can't see the T for the electrical box there, but then comes back here and can make another pass through the heat exchanger to pick up more heat from the boiler and so on, and then return this way back into the tank. See? Now, that's when the boiler is supplying heat to the tanks, in other words, storing the thermal energy. Now, you may say, well, why would you want to do that? Why wouldn't you just idle the boiler? So, you know, if you don't need heat in the home, just, you know, don't turn on the fan in the fire in the boiler and let it sit there. Well, the problem with that is that when the boiler out there is running, but it's not got full flow of air going in, what'll happen is it'll smoke a lot, and basically smoke is unburned fuel, and that's just fuel that I have to load and waste. Not only that, but that fuel then makes creosote in the chimney, and I would rather keep my chimney clean and keep the boiler running at peak efficiency, because what will happen when there is a call for heat from the home, the boiler, if it's on standby, and I didn't have these thermal storage tanks, when the boiler runs then and comes back online, it'll blow air in, but the fire's not real hot. And so it makes a lot of smoke, smells terrible, and finally, eventually comes up to temperature where it can supply heat to the home. By using these tanks, I can run the boiler at full tilt all the time, burn the wood as quickly as possible, as efficiently as possible, and basically just dump the thermal energy into these tanks. Now, these tanks, there's one on one side and one on the other. You can kind of see the send to one is here. It goes through the wall there. And there, kind of behind that pipe, is the other send. And then at the bottom, you probably can't see it, but there's maybe, yeah, you can see this one at least. There's a return coming out of the wall. So there it basically goes into the tank at the top, comes out of the tank at the bottom. Now, I don't remember why I told you all that. Something about the, oh, efficiency. So these tanks are very efficient because when I buried them below grade, I actually insulated them before I buried them on the ends and all around the bodies. Not only that, but then I piled dirt all around them. That dirt acts as insulation as well. So the tanks are actually very good at holding thermal energy and not letting it leak out, if you will. It's not the water that's leaking, it's the thermal energy. Now there is some loss, but the losses due to heat transfer from the tanks is less than the loss that I would have if I were idling the boiler, plus all the inefficiency of burning and all the soot and everything in the chimney would be a big pain. Now there's one more thing about this that's kind of interesting. When there's a call for heat and the heat has to come from the tanks, what will happen is I've got a bypass set up here. This is kind of the last interesting thing I'll show you. Let me get around to it where you can see it. I've got a bypass network set up here. The way it works is when I'm charging the tanks with thermal energy, water flows from the boiler, goes this way through this pump, and then down. So the hottest water is actually in the top of this tank on this side. There's a tank on this side, tank on the other side. So this tank holds the hottest water. So what I want to do when there's a call for heat and the tanks are going to supply the heat to the home, I actually want the water to flow out of here and backward. It can't flow backward through that pump, so I've actually got a valve there. It flows around through that valve and then here and serves to then go through this pump and then on over to the unit here where it's supplying heat to the home. So it's kind of like the boiler and the tanks are piped in parallel, where you can either run thermal energy into the tanks or you can run it out of the tanks and through this unit. So either the boiler or the tanks can supply heat to the home, or the boiler can supply heat to the tanks. So welcome to my messy basement. That's how my system works. I'll show you one more thing before I let you go. You can kind of see a little better the second set of ductwork. There's one set of ductwork coming off the top, because remember, air flows upward through this unit. So here's the ductwork that goes back and services the bedrooms and back of the home. Here's the ductwork that goes up. It actually jogs over just a little bit and then goes forward in here behind this concrete wall. And then of course it branches off there, and there's another one down farther you can't see. Similarly on the other side of the home. So the main trunk is really this back one here that's supplying heat to go forward into the home, because that's the bigger area of the home. And this is a smaller, the duct size is the same, but the ductwork coming off of this main supply here are a lot smaller than these are, because there's less area in the back of the home. So as far as increasing the efficiency of this system, my plan is to convert it to geothermal. So I will still have a heat pump, but my source of thermal energy will no longer be outdoor air. My source of thermal energy will instead be the ground, right? So 55 degrees rather than, say, 20 degrees outside. And in that case, I could run I would be free to run geothermal as much as I like, because I'd be removing thermal energy from the ground, which is consistent year-round. You don't end up with the same problems of frosting and having to run the heat pump in reverse. That really kills the efficiency of an air source heat pump if you have geothermal. So I'm looking forward to doing that. I'm also looking forward to getting that water heater hooked up so I can supply hot water from the boiler. I don't know if I will include a de-superheater on the geothermal unit. Probably should. That way I really just don't have to load the boiler if I don't want to. But, oh, one more thing about this. I keep saying I'm going to let you go, but one more thing about this that I forgot to mention. My intention is to leave the electric service hooked up to this system so that in the worst case scenario, I could have electric water heat. But the thermostats, which are inside here and at the bottom, I'm going to leave set at about 120 degrees. But when I heat up the hot water with the boiler, when I'm running boiler water through this to exchange heat to the domestic water inside of the tank, then I intend to heat up the water in this tank to about 160 degrees or so. Now, if 160 degree water comes out of my tap, I'm going to get scalded. So what I've done, let's see if you can see it. There's an air separator there, and you can't see it very well, but right here is a valve that's a mixing valve, and what it'll do, Oh, my heat's coming on. I hope you'll be able to hear me. What it will do is it will actually take the 160-degree water, mix it with cold water, and that way the water that actually supplies the home, which goes through here, will only be at about 120 degrees or so. And what that'll do is that'll increase the thermal mass in this tank because the temperature is so much higher. So I'll have a lot more thermal energy, and basically this small, I don't know, I guess it's about a 60-gallon tank. This small tank will act like it's about a 100-gallon tank, and I'll be able to have plenty of hot water for anything. But I'll still have efficiency, because if there's a case where I don't want to load the boiler, I'm relying on electricity supplying my thermal energy from my hot water, then what'll happen is it'll only go up to 120 degrees and hopefully not be terribly expensive. That's it, guys. That's my system. I hope you found this interesting, and I guess that's it. I look forward to seeing your videos. Bye.